G'day guys, welcome back to the third in this series of videos on computer and network systems. This one is all about network communications and protocols and means necessary for all of this communication to happen over computer networks. And so the first concept to understand in that world is the concept of a protocol. So that's a term that you need to be familiar with, and you'll hear a bit. Protocol is just a set of rules. It's just a way of doing things. There are protocols for all sorts of things. If you meet the Queen, you learn about protocols for how to greet her and how to act and behave and those sorts of things. They're just sets of rules and ways of doing things. Networks run on protocols. You can imagine computers globally all wanting to work in different ways, speak different languages if you like, when they're trying to communicate. That just won't work. For global network communications to happen, then the set of protocols that computers use need to be consistent. So that was recognised very early on when networks were being established, particularly in the process of developing the internet, and a standard set of protocols were developed, and they've been adopted as industry standards, and they've pretty much remained that way. And whenever any changes and things need to be made, then the same sort of process is followed. They're always global standards, otherwise this internet just won't work. So some of the main protocols you need to know about are obviously the big daddy is Transmission Control Protocol, Internet Protocol, TCP/IP, better known as. And that is the industry standard that was developed in the 1960s around the birth of the internet, and it's been adopted and changed ever since as well, a little bit, and tweaked, but it's pretty well, it is the standard by which computers communicate, or computing devices communicate on any network, including the internet. And really includes a suite of protocols. It isn't just one protocol. There are a number of protocols wrapped up in TCP/IP. Obviously, TCP being one of them, Transmission Control Protocol. Internet Protocol being another, which is the process of assigning IP addresses. We'll address that a little bit more in a little bit. HTTP being Hypertext Transfer Protocol. So that's obviously the protocol by which data is transmitted over the internet via websites. So you see that protocol on the beginning of every web address. DNS is the domain name system, a very important protocol, that one, that allows us to use friendly names to remember things rather than numbers all the time. DHCP, we'll have a little bit of a look at that. It's Dynamic Host Control Protocol. And then the Handshake Protocol we'll talk a little bit about as well. So starting with, I guess, one of the more important ones, and that being Internet Protocol. So Internet Protocol is what assigns unique addresses to every node on a network. For every computer network, if a computer is connected, or a computing device is connected to a computer network, it needs to have a unique address that no other node on that network has. So the IP address is the thing that was invented to allow that, to accommodate that. Currently we're at IP version 4, which was about the mid-1980s, dates back to about the mid-1980s. And it is a system of assigning addresses to nodes on a network where there are 4 sets of numbers. They're called octets because each number equates to a binary digit, an 8-bit binary digit, so an 8 for octet. So there are 4 octets. Each number in the IP address can be between 0 and 255. I won't go too deep into the reasons for that, but there's a sample IP address there, 172.116.254.1. So it's what's called dotted decimal notation, is the way IPv4 addresses are represented. They are 32-bit addresses because there are 4 octets, 4 8s to 32. That's why it's called a 32-bit address. And every node on a network using IPv4 would have a unique IP address. They can be set statically, so you can assign a specific address to a node. Most nodes on a network would be dynamically assigned their IP address via a thing called DHCP, which I'll talk a little bit about later on. But some common IP ranges there that you see in the table. Private networks, typically your home network is probably, if you looked at IP addresses on your home network, they'd probably be in the 10 dot range, or the 172.range or the 192.range. They're typically the ranges reserved for private networks. Our school network uses the 10 dot range. All of your devices have a 10 dot something IP address. Your home networks might be in the 172 or 190, just depends on what your particular router does. But all of those are for private LANs. Sometimes you might see a device get assigned a 169 address. That's called an APIPA address, or a private IP address. Essentially, an APIPA address is assigned when a node cannot find the network, cannot find DHCP server to get a valid IP on that network, and it just gets by default a 169 address. If you ever see that, that means that node, that computer, that device cannot communicate on the network that you're trying to connect it to. It just will not work. Something's gone wrong and need to troubleshoot what's gone wrong there. The loopback or the local host address is the 127. 127.0.0, usually 0.0.1, but that means that defines the local computer that you are using. That's its default address, the local host address, and we see that when we've done any work using dynamic web development, running web servers and things. See that address. So moving on, the problem with IPv4 is that it's running out. We're running out of addresses for IPv4. They call that IPv4 address exhaustion. So there are so many computers on the internet now that there aren't enough IP addresses to go around for all those devices. So that's been recognised for quite some time. And IPv6 has been developed, and a lot of ISPs are probably using IPv6 because it gives them more addresses available to connect clients to their internet services. Most local LANs are probably still using IPv4. Certainly we are. Certainly your home network is probably using IPv4 still. But IPv6 is essentially a slightly different system. It uses 8 groups of hexadecimal digits, so hexadecimal being a combination of the digits 0 to 9 and the letters A to F. And the groups mean different things. You can see in the little diagram there that it talks about 2 of them being a global unicast address. Some of them talk about what region that address is from, the customer, and then the last 4 sets of hexadecimal digits define the actual local network and the device on that, the individual device on that network. So these are 128-bit addresses. So you saw before an IP address, IPv4 address converts to a 32-bit binary number. These convert to a 128-bit binary number. So there are significantly more addresses available. And I'm not going to do the maths for you, but you can see there are 7.9 times 10 to the 28 times the number of addresses available in IPv6 as there are in IPv4. So if you do the maths on that, that's a lot more, obviously. And whilst these two protocols aren't really intended to be compatible, there are mechanisms that allow IPv4 devices to communicate with IPv6 devices so that actually can happen, and you can have devices getting an IPv6 address perhaps from your internet service provider whilst running an IPv4 address on your local network, because there is a distinct difference between what we call your internal IP address versus your public IP address. So you can see in this diagram here, we've got the router sitting here, which could be a home network, or it could be a more sizable small business network perhaps. But the router is performing the job of the modem as well and connecting out to the ISP to get the internet connection. And you can see there's an external IP address that gets assigned to your network, your internet connection, by your ISP, your internet service provider. And that would be different to what that device's IP address would be on the local network, on the LAN, inside the little dotted box there. To the rest of the world, they see you as your external IP address provided by your internet service provider. However, to your internal network, to your home network, or whatever this network might be, it sees that device as the LAN device, the private LAN private LAN IP that's been assigned to it. So that device that's providing your network connectivity would have 2 IP addresses, one external and one as its internal address, and then all of the other clients on that LAN get addresses in the same range as that. So you can see in this example, you've got all of those other clients with 192 addresses, which is in the range provided by the DHCP server running on that router. So that's the difference between internal and public IP addresses. So how do devices get given an IP address? Well, mostly they are dynamically assigned, and that is the job of DHCP, Dynamic Host Control Protocol. It's actually a bit of software that runs usually on a server. In the example previously, in most home networks, your DHCP server is probably running from your router, from your Wi-Fi modem router. And there's a system there assigning IP addresses to devices that want to connect to your network. As part of that process of connecting, they get assigned an available IP address in the range for your network by that DHCP server. And the DHCP server just maintains a database of all the IP addresses in the range for your network and which ones are used and which ones are available, so it knows which ones to give out. Obviously, it needs to give out a valid one that's not in use in order for your device to connect, because they all have to be unique. So clients typically on a network get assigned an IP address for a certain period of time. That's called a lease period. So that could be 24 hours, it could be up to a couple of weeks. The default's usually about 8 days on most Windows networks anyway. And after that time, the client releases that and requests a renewal of their IP lease, and depending on what DHCP does, it may renew the lease on the existing IP address and it doesn't change. Or that client could get an entirely different IP address. That is very possible. It's dynamic. It can change. In certain situations, though, you want to set an IP address on a client, on a network, on a node on a network that does not change. And that's called a static assignment, a static IP. You set that on the client device and it's permanently set, and usually would then be reserved by the DHCP server, so it doesn't get issued to any other devices. But that's the job of a DHCP, and on your home network, your router is probably performing that function. So in terms of sending data around the network, the concept was mentioned very briefly in the previous video, I think. We break data up into little chunks called packets to transfer it around your network, whether that be on a LAN or whether that be over a WAN or even over the internet. A typical packet has a few bits. The payload is the actual data that's being sent. But in order to get that data to where it's got to go, the network adds a header to that data packet that contains the address of the network that it's trying to send it to. So if it's on the internet, the address of that WAN, and the actual address of the client on that network that made the request. So that's how our networks know where to send data packets and what the destination is. And then there's a trailer on the end that identifies when all the data has been sent. So networks are smart enough these days to know if not all of the packet arrives, I haven't got the trailer, it hasn't all arrived, send me a request back to say, hey, I didn't get everything, please try and send that again. And this all happens pretty quickly, all over seconds, milliseconds in fact, on most networks. But that's the concept of packet switching, and breaking data up into packets and sending them often along multiple paths. So this diagram just shows how that might work. If you've got, and this is intended to be on the internet, but it could be elsewhere as well. One sending device on the left here, sending a packet or breaking a full lot of data down into smaller packets and sends them out individually addressed, and they can take very different paths to their destination. Because they can hit routers all over the place. They don't necessarily all have to follow the same path, and on the internet that's pretty typical. That's why websites sometimes load in little pieces. You see as it receives packets from the different paths that they're taking from the sender to the destination. You can see at the end, at the recipient end, all of those packets are then reassembled. And they're received using that addressing information, as I spoke about just earlier, and then they're reassembled at their destination. That's how they get there. Domain name system, DNS, is another of the protocols to be aware of. And domain name system is what was devised to mean that we humans didn't have to remember all these IP address numbers, because that's hard for us. It is much easier for us to remember names and words. So DNS is a system of representing those IP addresses using more friendly word names. And you see this typically on the internet, but also on networks as well, where you might name a server. Rather than remember its IP address, you can remember that you called that server Fred. And so it could be much easier for you to remember. So the example here is the Google domain. Google.com is a domain that you would buy and register, pay money for, and that then equates to an IP address behind the scenes. It's easier for us to remember Google.com than it is to try and remember whatever the IP address that relates to. For this to work, a LAN must have a DNS server running, which again is a bit of software that would be running on a server somewhere to allow this to work. And there are also DNS servers on the internet that you can, rather than run your own, you can point your network DNS at these servers on the internet, and they maintain big databases of what domain names are in use and what IP addresses they relate to. And finally, the final protocol that need to have a little bit of knowledge of is about wireless. So obviously wireless is a massive thing in our modern world. Most often our devices will want to connect wirelessly to networks, and the wireless protocols are all governed by an organisation called the Institute of Electrical and Electronics Engineers, or IEEE, which is something that you may have seen on other types of devices. There are a few standards that they control, Wi-Fi being one of them. The Wi-Fi protocol is known as 802.11. That is the Wi-Fi protocol, and there have been many variations as Wi-Fi has improved and speeds have improved and the number of clients that they can support has improved. So the legacy no longer used, just standard 802.11 isn't really available anymore. But as Wi-Fi has improved, the standard has changed. We've gone from 802.11a to 802.11b to G to N, and now the current standard is 802.11ac. And you can see the frequency has changed a little bit as we've gotten faster. Now the AC standard uses a 5 gigahertz band, and as those speeds have increased, the maximum data throughput of those standards has gone up. So the theoretical throughput of an 802.11ac network is 1.3 gigabits per second. That's obviously theoretical. You typically don't get that full throughput, but you certainly do get considerably more than you got from a theoretical maximum on 802.11n, which was 600 megabits per second. So we constantly improve the wireless standard all the time. And I think that's all you probably really need to know about network communications protocols to be able to do some basic networking exercises.